impedance circuits. Transform impedance circuit. Impedance circuit. I'm covering here theoretical part. If time permits, we'll go through a few of the examples. But today, majority of the part I'm going to cover of theory. So we already know Laplace transformation. So when you say Laplace transformation, we are writing that thing in, suppose if I say V equal to IR. And if you wish to write this thing in time domain, that we are writing like VR, this is related to time domain, that VR of t, writing R. So we are normally writing in a small I R into t. This is in time domain that we all aware about. So when you are converting this in a different domain, like a Laplace conversion, that is a transform equation that is known as transform equation. So this one is in time domain. And when you convert this in Laplace domain, it is going to be converted in frequency domain. So suppose we are taking it as zero initial condition. Can anybody tell me what is the meaning of zero initial condition? कोई बताएगा? Please tell me what is the meaning of this. Suppose zero initial condition.
Sir, the elements are uncharged initially.
Yeah, the meaning of this zero initial condition is no charge present in any of the passive element of the circuit. Okay, that shows a zero initial condition. Now, when we do a Laplace transformation, like suppose here I'm writing frequency domain. That is, normally we are working on a Laplace transformation. So we can write the same equation, voltage across resistance. Here we are working on the resistance part, resistor. Element we are working on, that is a resistor. So we can write for that is VR, that we are denoting in a VR of S. This is how we are working on. And this one we can write R, IR of S. That we all aware about. And here you can write this term IR of S equal to VR of S upon R. Is it okay with this one? We are not getting any kind of charge stored in the resistance. That is why directly we are writing this one, where we do not have to worry about any condition. So you can write, when we are working on impedance transform, same circuit, we write R equal to VR of S upon IR of S. That can be also written. And this one is known as impedance of that element. So impedance in our case, that is equal to a resistance value. There is no any kind of other effects. And when you say admittance, and that is denoted by, this is impedance, its reverse is admittance, that is denoted by capital Y of S. Here we are taking for resistance, that is why I have written capital R here. So that is inverse of the impedance. Inverse of the impedance. So that can be written as, when you write this, that can be written as admittance, admittance YR of S equal to, that is 1 upon impedance. So that can be written as IR of S. That will be reverse. So you remember the equation of this resistance, or you can say impedance, admittance. Okay. So now when you draw the same circuit for this one, when you draw the circuit, conversion circuit, then we can draw like this way. I'm drawing here. First circuit, this is, don't draw this, just when I complete this, then only draw this one. Okay. Otherwise, I'm going to erase something in this also. Just drawing it because it looks similar. That is why I'm drawing like this way. Okay. So here I need to remove this part. That is not working. This one. This is going to be removed, and here also this is going to be removed. That is nothing but a resistance. Here is resistance, and when you are writing for time domain, that is VR of t. Initially, this is what we have written, and this is current flowing through that resistance in time domain. Now, when you convert this, when you convert this one in Laplace domain, this element, we are converting this one. We are converting this one in impedance. So that is converted to VR of this as VR of S. And this side is a positive, this side is a negative, here is a positive, this side is a negative, and this current flowing through that is written as capital, sorry, this is I've only written VIR of S. Yeah. And when you write this thing in admittance, like first one we have written like this way, this is the circuit where you can write transform impedance representation. Transform impedance representation. And this side also we can write, but in admittance form. So that can be written as, this is IR of S, this is VR of S, this is plus, this is minus, and that can be written as YR of S, that we know conductance, or here it is written in admittance, that is G. Conductance is written as G, and that is equal to 1 upon R. In our case, this YR of S, that is nothing but 1 upon ZR of S, the inverse of impedance. So this is how we can convert, transform admittance representatives. This is transform admittance representation. Okay, so this is how we can able to convert. You remember this. These are the things are useful in when you are working on the examples. Okay, so these are very much useful. So this is all we have written for the resistance. Now the upcoming element, that is we are going to work upon inductance. The second is inductance. So
Sir,
all we, yes,
so can you go to the last slide, please?
yeah. Any doubt, or you are writing this?
The writing there.
Okay. So this is just a conversion. This is in time domain. Writing for time domain. This is for time domain resistance representation. And yeah, anybody having doubt in this one? Any doubt? This is basic Ohm's law kind of equations. Now, and anyone can tell me what is the voltage across inductor? Voltage drop across inductor. The equation I'm asking. Voltage drop across
Sir,
inductance.
L di by dt.
Voltage drop across. It can be voltage drop, or you can say current stored. When you write equation for the current stored, we write that current stored, charge stored. Voltage drop across inductor. Yeah, what was the equation? Suppose if I say in time domain V L of t, somebody say L di by dt. Yeah, it is the correct. L dil by dt. IL I have written small il. These all things are representation in time domain. Now suppose I'm writing the equation of IL. If I want that IL, I have to remove this differentiation, so I have to take integration. So the current through the inductor at time t, or current stored in the inductor at particular time t, that can be written as by doing the integration. So when you do the integration of this one, that can be written as 1 upon L, the starting integration from minus infinity to t. It might be possible that this inductor is having some charge stored, so that we have to write starting limit minus infinite, and here VL of t dt. Okay, so we can able to write this equation. But suppose we think that there is some charge already stored in this. We are taking that condition. So at that time, this IL of t will become a little bit different. So that current we always know that is a IL0 minus, that is stored before time t start. So that was the charge stored in the inductor. So that is, I am writing this, and that can be added in the equation of, so this now time will start from 10 0 to minus limit. It is not minus infinite, that is already added. So time will start from 0 minus just before the switch is closed. That kind of thing we can say. So here it will be the same equation, VL of t dt. Okay. So where you can say, where this IL of 0 minus is nothing but initial current stored in the inductor. Yeah, anyone having doubt in this one? Let me know. This is, we are representing of current and voltage across inductor, current through that inductor in a time domain. This is all we have written for the time domain. Now we will work for the Laplace conversion, Laplace transform, because we are working for transform circuit. How that after transformation, how that element behaves, that we are writing. So few of the behavior we have already gone through, already represent that circuit, that initial when time t equal to 0, how that circuit behave, how that element behave, open circuit, closed circuit, current store, voltage across, all of these things we have gone through. But little bit explanation, I'm showing you that part. Now we are working, I'm going to write the equation when I transform this circuit. So when Laplace transform, so this VL of S, when you do the Laplace transformation of VL of t equation, excuse me, that can be written as this equation I have already shown you. that can be written as this. Okay, we have already gone through this equation. So this voltage across that inductor can be written in the transform way, that is L into bracket S ILS minus IL 0 minus. And when I write like this way, we can write it as L Vs of S minus L IL 0 minus. Just simplifying that, and Is of S equal to VL of S upon SL plus IL 0 minus upon S. This is what I simplified. I take this Is other side and taking that IL 0 minus in this side. And finally, I can get this equation. So now assume we have already initially said that for the all of this equation, for zero initial condition, we are working on the transform circuit, but we are assuming here for the zero initial condition. If we are taking this zero initial condition at that time, we can say IL of 0 minus will be 0. So if you put that value here, like here in this one, if you put that value here, you can write that IF of S equal to VL of S upon SL. That time you can write VL, that voltage across inductor. Yeah, here it is a little changed. Yes, this one is L. This one is L. Okay, so that can be written as IL as, this is a capital L I'm writing here. So that voltage across inductor can be written like this. Now, we already know that when you're writing impedance of any of the element, here if I wish to write the impedance for this one, for this equation, how I can able to write impedance for inductor? What can be the equation from this? Can you tell me what will be the impedance equation here? Impedance of inductance, that can be represented as like ZS of S. And let me tell you here, it is very easy. We already gone through the resistance point. In resistance element, we already gone through this. So that is V by I form. So that is VL of S upon IL of S. So in our case, that is, if you take this IL this side, only LS will remain this side. Okay, so this is the equation of impedance. Remember this for inductor. And if I want to write the admittance equation, admittance of inductor, that is the inverse of impedance, that can be written as capital L of S equal to IL of S upon VL of S, and that can be written as 1 upon SL. Okay, so remember this one also, this is going to be useful. So let me draw all of this. I'm just going to draw this, all of this. So okay, when you convert that, you're going to convert that element into a transform impedance and transform admittance circuit. I'm drawing three of that circuit, three of that element. First is in time domain, then I transform impedance and transform admittance. So all of the three we have already seen for the resistance. Here I am drawing for the inductance. Okay. So here this one, you see, we are working for the inductor. So this is inductor capital L. Current flowing or current stored, I can say that is stored current is nothing but IL0 minus. This is IL of t, time t. This current is flowing through the inductor. It is VL of t. This is in time domain representation. Now, when you convert that in transform one, see the equation that is VL of S inside plus current flowing that is capital L, and this one converted impedance that we already written, and that can be written as ZL of S equal to SL. Okay, this is okay for I can say when initial condition considered 0. Now suppose I am not considering initial condition 0. You can apply your KVL here. You can easily apply KVL here. You'll come to know the equation. Let me show this one. If you apply KVL here, what you're going to write? That VL of S equal to Z S into IL of S. This you can write. This you can write that is SL IL of S VL of S. This equation, see this equation properly. This is showing you the SLILS. I'm going to show you that last slide. See this equation. SLIL. This three element we are writing. Here we are considering this is 0. Now if you think this element is not 0, so see this, when you return this equation, that element is not 0 here. So when you are converting without 0 initial condition, you have to add one element here in this part. So that can be written here without 0 initial condition. So that amount of voltage that can be added here, that is a stored one, that is I am writing here L I L at 0 minus. Okay, this is what I'm storing and writing that. How I have written this? This is from the equation we have derived for the without 0 initial condition. So when you apply here, let me apply the KVL here. When you apply that, you can write VL of S equal to ZL of S into, sorry, that is IL of S plus, this is plus minus plus, so here will be minus sign, minus LIL of 0 minus. See this equation and over this equation, both the equations are equal. Over there, whatever you have written over there, it was nothing but Z as we have written, without a charge store. This is what over there in our equation. So here it is. If you put at this place, set it up as ls. So both the equation will be equal. Both the equation will be equal. Okay, understood or any doubt in this? If you are having any doubt, you can let me know. You remember this one, huh? How to remember these circuits? First circuit, converted one, in transform, Laplace transform, in admittance form, sorry, in impedance form. Now third is an admittance form. So when you do this one, this will end up there. So we have to write this admittance as that is 1 upon SL, like this way. But when you are considering this admittance is how to take a parallel source, current source, and that will be IL of S upon S. From where we have taken this, if I tell this, from where we have taken this is we have taken from the equation of current. Let me show you that one also. See this part. So from this one, we have taken that current. So when you are working on admittance parameter, when you are working for admittance parameter, you have to consider the KCL. You have to consider the KCL. Okay. So when you consider the KCL, at that time, you always see the current distribution. The current total current is summation of two currents, that V by L form in IS. So if I show you that one in this circuit, here it is distributed in two ways. This equation can be written as the current going through this way that can be divided in these two parts. This is nothing but capital U of S. That can be written as IL of S equal to nothing but V by RV is nothing but VL. No, that's not wrong. This is admittance, so its reverse is SL, right? So that is a Z of L. That can be written as L. And this is another current IL of 0 minus upon X. So from this circuit proves the second equation of current. So from that one I have from this one, and from this circuit I have solved this equation. Okay. So this is how we convert one, and this circuit is for admittance. Third one is for admittance. Second is for impedance, and first is showing in time domain. Yeah, anyone having doubts, just let me know, so that we can move for the third element, capacitor. Yes, anyone having doubt? Is it okay with this? Just tell me yes or no. Are you there? Is it okay with this one? Am I audible? Okay. So let us go for the third element, and that is nothing but capacitor. Third one is capacitance. So current through the capacitor in time domain. Yeah. Can anybody tell me the equation of current through the capacitor in time domain?
C dV by dt.
So very easy. C dV by dt. Correct. And when you do the integration of this one, you can able to find voltage across capacitor is equal to 1 upon c minus infinite to t. We have taken this minus infinite that you already know, because it might be possible that capacitor having some charge at before the switch is closed or before source is applied. So we can write for this one, when you say charge is stored, that means some voltage might be present already in that capacitor. So we can write this one Vc of t, that is nothing but this way also we see 0 minus plus 1 upon c 0 minus 2t I of c dt. Okay, so this is what a representation of voltage and current for the capacitor in time domain. Now we'll check for the Laplace transform, but we'll also consider for zero initial condition. So taking Laplace transform, you can write that I c of s equal to c into bracket s vc of s minus vc of 0 minus. This equation also we have already shown this one, and that can be written as, if you simplify this, vc of s, I'm just multiplying c inside, you can write c vc 0 minus. Okay, this is what a current through the inductor. We can take this vc of s on one side and we can write the equation of vc of s equal to vc0 minus upon s plus 1 upon c I c s. Okay, with this, now what we will do, we are going to consider zero initial condition. So when you use zero initial condition, means at that time no charge stored in the capacitor. So stored charge is nothing but this one, and when you take this element, this parameter 0, you can write the equation for Vc of s upon, this is Vc of s equal to 1 upon c Ic of s. Now you see, you need to write the equation of impedance for our case capacitor. Now tell me directly, you can say from this one, impedance equation for capacitor when zero initial condition we are considering. Tell me the equation of impedance.
1 upon CS.
1 upon cs, correct, because v by I, if you take this I this side, you can technically write 1 upon sc or 1 upon cs. Okay, and the reverse of this is a admittance, that is c of s equal to sc or cs, that you can say. Okay, you can say, you can see here. Okay, so this is for capacitor. Now we can write the element circuit, but how we can able to convert these things. So if I draw these circuits, first one in time domain, I connected the capacitor, current through that is IC of t, this is capacitor, VC of e plus minus, this is time domain representation. Now the second one, here if I draw this, yeah, suppose initial charge is present. Initial charge is present. Now what should I write here? What should I write here? Can anybody tell me? Means already some voltage VC 0 minus is already stored at that time. But this is this is Z of ZC of S, and that can be written as 1 upon SC. That already derived. Now see the last equation. From that one, can you tell me what should I write here? Charge is present, that is what we are considering. If the charge is not present, we can directly complete this one. But with the charge, I have to write something. You see, initial condition is not zero in our case. What should I do? Should I connect current or should I connect voltage? Source or current source? We have connected the voltage source in the inductor circuit, inductor part. Okay, let me show you the equation. See, we are working on this equation. You have already written this one. This part is already done. This part. Inverse circuit, I can show you that. Here, see, this part is already done. When you are writing the equation of this is capital IC. So if I put like plus, this is plus, minus. I'm not writing anything right now because we need to find it. So I can write the equation like this way. VC of, this is not T, sorry, this is of S minus ZC. I'm writing directly at the place of ZC of S and YS. Directly I'm writing I of S. This is also S here. This is T upon SC. Now this part is remaining. Now see that equation. So we have written VC of S. Then after this was this side minus IC of S upon SC. This is if I write this side. If I write this side, see this part, this side, that can be written as voltage supply. Tell me the sign. Tell me the sign here. This is VC of 0 minus upon. Yeah. Tell me the sign here. Plus, minus, or minus, plus?
Plus.
Like this. If I write like this, it will become here. If I complete the equation, VC 0 minus upon equal to 0. And if I simplify this equation, it will become VC of S equal to VC of S upon C plus VC of 0 minus S. Now you compare both of these equations, this equation and this one. So here also plus sign, here also plus sign, this VC of S. And now it is become equal equation. No difference in both of these equations. See, this one is also same like that equation. So our consideration is totally correct here, plus minus sign. If we do the mistake in this one, our answer will be different. Our equation will disturb. Here if I put this minus plus sign. Here will become plus sign, and here it will ultimately minus sign. And that will make this circuit or this equation different than whatever our assumption is. Whenever you see this one, this equation should be matched by, this equation should be satisfied by our circuit. Otherwise, it is going to make a wrong answer. Understood this one? You see, this is not the same as in the inductor. If I show you that inductor circuit, here see, this was minus plus here, and from that we have derived this equation. So we are also satisfying that equation in this one. So here it was minus plus, and in our this case for the capacitor, here it is a plus minus sign. It is a little bit different, okay? So remember this polarity, otherwise you are going to get the wrong answers. Understood, or should I explain once again? Understood? Is it okay with this? So we can draw the third one. This is the third with the admittance. Admittance part. So here is the admittance YC of x, and this plus minus VC of s, and current flowing through, that is nothing but IC of x. When we are taking this admittance part, you have to add the current, and that current is divided into two sides, and that source is nothing but current source is acted in parallel. So that can be written as CV0 minus. Okay, so this circuit, third circuit is showing this is using KVL. This is KVL. Here you can apply KCL. When you apply KCL, let me show you the equation of current. When you apply KCL, this need to be fulfilled. This need to be fulfilled. Okay, otherwise your answer will be different. Is it all right?
Sir,
Yes.
sir, in the third circuit, the polarity of the current source will be opposite.
It should not be a downward side. Is it like that?
Yes, sir, it should be upwards.
Yes, it should be upwards. Otherwise, that current will be added and our equation will not be satisfied. This should be upward side. So our equation, this will be minus over there. So this one plus this one, if you satisfy this one, you can write like this: IC of S plus VC of, sorry, this is VC 0 minus VC. Here is VC 0 minus, and you can write this VC 0 minus x into C into VC 0 minus equal to the current flowing through this way. So this is impedance, if you say 1 upon SC into current. So that is nothing but I C of S. We are writing for the current, so that will be equation. If you see the equation of current, that will be, tell me what will be the current here. U of S upon this one, this part. This is the current that can be written here VC of S into SC. Okay, so this is how we can write V by R form. V by R. V by R means V by impedance. Okay, and this equation will become, our equation will become IC of S equal to VC of S SC minus C VC0 minus. And this is satisfied equation of current through the capacitor in Laplace transform. Okay, understood. So three of the elements we have discussed, and after this we are going to work upon few example. I think time is very limited to us. So we are having a limited time, a few minutes only. So I'm stopping here. We'll continue. This theory is already done. We are going to check few of the example based on these conversions. Okay, if anybody having doubts, just let me know on this one. Yes, once again I'm going to check the attendance.